Hi again. We're going to move into the new chapter. This is literally the material now from chapter 13, which is about Thevenin equivalent circuits. Now, you probably haven't heard of those before. I'd be pretty shocked if you had. But they are a very useful tool, and they're one of a family of simplifications that we can apply to circuits. There's another one, there's a Norton equivalent circuit. That's one that's mentioned a little bit. We don't have time to deal with that one. The concept is very similar, and so it's not worth doing them both. So we're going to focus on Thevenin equivalent circuits. So what does that mean? Before we get into the specifics of a Thevenin equivalent circuit, I think it's really important to come back to a couple of words that we've tossed around at various points. There's three E words that you could say are very important in our field. One of them is called equality, and that's a simple mathematical concept. One is equilibrium. We've certainly talked about a number of those. And finally, equivalence. So what is equivalence? Now, you can picture equality being a mathematical expression. So here you see a simple expression. If I have $10 per hour wage and I work for $10, I earn $100. That's just an equality, very straightforward. An equilibrium is how I manage my money and how I earn about as much as I spend so that I have an overall balance between my income and my outlay of money. And that's equilibrium between those two economic forces. Now, what's the equivalence going to be when we think about money in this case and currency? Well, it's currency. It's the equivalent currency in other denominations. So, of course, American dollars are not the only currency you've heard of, and there are euros. That's another very important one. And there's a conversion rate that you can look up at any moment in time. It's changing, of course, constantly. And the equivalence then is to say that, that dollar, in this case, I've looked up a value, it's approximately correct, is worth 0.93 euros. And so that tells me those two are equivalent. And what does that mean? Well, it's hard to know sometimes exactly what they mean. I mean, you can go to the bank and you'll get that amount of money for it. There's some notion that in some macroeconomic sense that they have equivalent power, the equivalent buying power. They mean the equivalent amount of wealth. And that's very vague, of course, sometimes to figure out. And you've probably heard of people who make money trading on different currencies and trying to work the conversion rates in their favor. So this equivalence can be a little bit of a vague concept at times, and we have to define it quite carefully before we go ahead with it. And that's very true in this situation of the Thevenin circuit, because the Thevenin's theorem literally reads, insofar as load is concerned, any one-port network of resistance elements and energy sources can be replaced by a series combination of an ideal voltage source, Vs in this case, or VTH we call it, and resistance, RTH. So the Thevenin voltage, the Thevenin resistance. Now this is maybe hard to parse right away, but it's actually very powerful because it says any more or less complicated circuit that we want, we can replace with a very simple circuit that has one voltage and one resistance. And that's powerful, and that's an equivalence. And so in what context do we picture that equivalence? Well, we conceive of that equivalence as seen from the outside of the circuit, as seen from a load. So we've talked a little bit already about loads. So loads are what you connect to a circuit. Loads are the speakers you connect to an amplifier. Loads are the oscilloscope you connect to your measurement circuit to measure an ECG. So anything that attaches to the circuit and hopefully does something useful. So equivalence is what that load sees or senses or has at its disposal in the way of current and voltage. That's equivalent, whether you have the original circuit or the Thevenin equivalent circuit. So that's arguably pretty powerful equivalence and pretty useful one. So as long as we can now determine the Thevenin voltage and the Thevenin resistance, that's the catch, of course. As long as we can determine those, then we can replace sometimes very complicated circuits with remarkably simple ones. And so, one way of capturing this equivalence is to say that no amount of experiments on the terminals of a circuit can tell the difference from the Thevenin equivalent. So if I'm measuring on the terminals of that circuit, and it's called a one pole because it only has two contacts, that's a one pole. It's another circuits term that you may encounter in the future, and we heard about it in the Thevenin's theorem, in the original form of it. And so the terminals of that circuit feel, look, through any experiment you want to do, the same, whether you have the Thevenin equivalent or the original one. Now, how do we create, or how do we determine what the Thevenin voltages and the Thevenin resistance are? And so it's actually quite simple conceptually. The Thevenin voltage is the open circuit voltage of the circuit that we're trying to simplify. So if we can figure out what the open circuit, which means without a load, if we can determine what that voltage is of that circuit, then we can say that's the Thevenin voltage. We have it. And similarly simple, we can say that the short circuit resistance, and we'll get into exactly what those mean, but you can sort of picture it's the resistance that we have when we short out all of the sources of energy, when we short out all the batteries. So essentially remove the batteries, replace them with a wire, and then look into the circuit and we determine what is that resistance. So that's the short circuit resistance of the circuit. And if we can find our open circuit voltage and our short circuit resistance, then we can write the Thevenin equivalent. It's kind of magic, and we won't have time to go, of course, into all the theory and background for it, but we'll move into some examples, and I think they'll make it quite compelling. So we can look at some very simple ones here. Here's a picture where we say find the Thevenin equivalent of the following circuit, and you see that there's a quite simple circuit there with a voltage and two resistors. And to figure out what the open circuit voltage is, we simply solve for what? A Kirchhoff's torr, of course. So we can do a Kirchhoff's torr around that loop and figure out what is the voltage across that resistor at our output ports, that resistor that we are calling R3. And so that voltage across that resistor is our open circuit voltage. Now, we can be smarter about this because we've seen this kind of circuit before. We've seen it in the bioelectric measurement circuit where we had VECG, we had the resistance of the electrode and the resistance of our multimeter or voltmeter, RE, RM, and we were able to just write down what the voltage is on the voltmeter as a function of the two resistors in that cascade, in that series connection. And here we have a series connection as well. We have the RP and the R3, and we can say those are our two series resistances, and we can just write down what the voltage is. It's the product of the source voltage, Vs, and R3 over R3 plus RP, and plug in numbers and actually get a value for that. So that's actually remarkably straightforward, and we'll see this not always quite that simple, but in lots of ways we can actually simplify resistors, and we'll go through that in some of the discussion sections and be able to create very quick equivalent circuits or equivalent voltages for that open circuit voltage. Now, what's the short circuit resistance? Again, we short circuit the voltage supplies, so that Vs becomes a wire in our diagram. And if we look at that, we now have RP and R3. And if we sort of imagine moving RP around to the end of the circuit, then we see that RP and R3 are parallel. They're a parallel circuit. And we know already we can simplify parallel resistances. We learned it in the flow context. We can do it in the electrical context. So we add the inverses of the resistances and then take the inverse of the result. Or, this is the direct route, we take the product of the two of them over the sum of the two of them. You can go through the math, and again, we'll cover this in the discussion sections. Very straightforward to show that the product of the resistors over the sum of the resistors is the equivalent resistance for that parallel circuit. So we can pretty quickly write a single equation, solve it, and find out what the equivalent resistance is, as we do here. And then we can replace that other circuit with a, arguably somewhat simpler one. We haven't saved a lot in the way of simplicity. This is just an illustrative example. But we can see that indeed it is a simpler circuit and an equivalent circuit, and that's really the important part. So that's really the starting point for Thevenin circuits. Again, it has this sort of element of magic, a little bit like op amps, but if you just go through a few examples and see how it works, you'll be able to execute it at least, and hopefully you'll see in this problem especially why it can save you time, why it's an efficient way to go about looking at circuits and saying, I have lots of sources and complexity and resistances, I'm going to combine all those into something much simpler, and that will make all the subsequent calculations or evaluations of that circuit that I need to do much simpler. And so it's a powerful tool. Thanks. Talk to you soon.